Okay. Hello all. Yeah, perfect. So this is for section 13, section 14, 17 and 18. We are studying transformer, and let's have a recap of whatever we have learned, and then we'll go ahead. So quick recap. Transformer, already you know what is a transformer, and in fact I bought a transformer today. I'll for one of the sections, I think two of the sections I have shown this. I'll again show this somehow, when they will show the screen, and then I will show to try. What is a transformer? I'll first try to draw something like this, a block, a box kind of thing. This is a new system that I am trying to accustom. It will take some time. So for a transformer, you can imagine a box like this. Many of you who have done experiments seen transformer. You have some nameplate over there that tells you details of the device. You have you have the terminal, say two terminals one side and another two terminal on the other side. So you can think of another two terminal on the other side. When you make connections, you can just connect this wire from this side to this side, one side, and then you can connect the other side, this side to this side. So one side is input, another side is output. By the way, now it can be shown. So this is a transformer that you can check, and so you can check. This is the device that we are going to study today. This is one side. You can see the wires are coming here, right? And this is another side. You have three wires here because we have a tapping here, and then we'll discuss tapping and all in later classes. We can see that the winding, transformer has winding. This is a winding. You can clearly see this is a winding, and this is a core. This is a core. So wrapped up. When regular classes will start, and then we'll try to pass to you, and then you can touch and you can see. By the way, this is just a very small transformer, very small rating. Transformers can be huge, really. You know that. In the power transmission systems, we use huge rating transformers. Transformers are used in the generating stations to step up the voltage, and in the transmission lines, we get the power out, and the distribution, the substations, you have again step down the voltage, and then we use that. So in our electrical systems, we use many transformers, and there are transformers which are used for different other purposes. When we discuss, we'll come to that. Now quickly, we can imagine like so this is one side, so you can think that this is one side and this is another side, all right. So we can say that this is the input of the transformer, so we can write that this is input of the transformer, this side, and this is output of the transformer, this side, input side and the output side. Both input and output side, input is electrical power, so you can see that power input here you can write, output is also electrical power output there. So transformers actually transforms electrical power at one voltage and current level to the other voltage and current level, right? And in between you have electrical isolation. There are transformers which are used as isolating transformers, where the voltage and current levels are same, and there are transformers which are called as auto transformers, where the electrical isolation is not there. We'll study all one by one, but for the time being, you have an input side and an output side, and then you can check here for this fellow. You have a nameplate. So whenever you try to understand a device, you have to look to the nameplate for information as what could be there. In the nameplate, what are the informations that could be there? So if I go to the next slide, sorry. So this will be there. I'm sorry, I'm very new to this. I will just try to gradually we will learn. So now, what is there in the nameplate of a transformer? What informations are there? So nameplate details, we are trying to nameplate. So nameplate, what is it? Nameplate is like your I card. If all of you have identity card and there you have the name, a lot of informations you have. Similarly, for the transformer you have voltage levels, say V1 one side and another side V2. You will definitely have voltage levels for the transformers, input side, output side. And you have kVA, so you say S, suppose we say S, which is basically, and in bracket we can write as kVA, kilovolt ampere, volt ampere rating. You have volt ampere rating over there. And then you have transformers, can be single phase, can be 3 phase. Say we are studying only single phase transformer for the time being, say single phase should be there. 50 Hz, our power frequency is 50 Hz, so 50 or 60 Hz, that information, and there are some other informations too. Right? When you have these informations, then you need to understand. Say for example, let us take a concrete example. Say we have 11 kV, a transformer 11 kV by say 440 volt, 440 volt. Say 100 kVA, it can be 100 kVA, it can be single phase and 50 Hz. 50 Hz. Suppose these informations are available in the nameplate. What do you understand? Clearly, there are two sides. One side is rated for 11 kV. Sorry, I have pressed something else. Okay, so one side is rated for 11 kV. Another side is rated for 440 volt. If I put two windings, transformer has. If I put just for the time being, just two windings. What are these windings? Will should learn. So suppose this is 11 kV level, and this is definitely high voltage compared to that. So we say high voltage level. This is 440 volt. So this is 440 volt. This is compared to 11 kV. This is low voltage level, right? We say this is low voltage level, right? This is there. This is single phase, 50 Hz. Those informations will be there, and this 100 kVA. So that kVA decides the current rating of the winding, and these are all rated conditions, right? All these values are for rated conditions. So the transformer is rated for 11 kV, 440 volt, 100 kVA, single phase 50 Hz. Single phase 50 Hz, that's a single phase system or 3 phase systems. All right, 50 Hz is corresponding to the grid frequency. But how would this 100 kVA? Volt ampere rating of the transformer, and why it is volt ampere rating, and how we can find the current rating from the volt ampere rating. This is simple. If we go to the next page, then we will see that, well, coming back again, V1 and V2 and S kilovolt ampere, so volt ampere rating we have, right? So this is S, we can say this is S, this is volt ampere rating, and then obviously you can calculate I1 here, current rating of the V1 side. If I assume that this is my high voltage side and this is my low voltage side, right? I1 you can calculate. How about I1? I1 is easy to calculate. You have S volt ampere divided by V1. Simple. How can you calculate I2? You have I2, you have S volt ampere divided by V2. Right? So you can just put values over here, say for the last data that we put, say 100 kVA and then 100 and 1000 and then put V1 11 kV, and then you can calculate I1 current and I2. You can clearly check volt ampere being same, right? So volt ampere being same, S and S, right? On the high voltage side, say 1 is now our high voltage side, the current V1 is high, current will be smaller. High voltage side current will be smaller, and similarly for the low voltage side, V2 is small, so S is same, so current will be higher. So whenever you design a transformer, you make a transformer, you have to take care of all these things, right? So I will just, for the sake of completion, I just complete it. So this will be your the I factor. Anyway, so this will be your I1 and I2. So, when you make a transformer, you have to really take care how do you decide the winding. Transformer have 2 windings, and then take care. Principal operations we will soon learn, and then we will check over there how to take care. Okay. But now the transformer is rated for, on the high voltage side is rated for this current, on the secondary side, on the low voltage side, right. It rated for this amount of current. And by the way, you have already listened that I told primary side, secondary side. What about this? To tell you very frankly, for a transformer, what is unique is high voltage side and low voltage side. So, you can clearly see transformer has 2 windings, and then if I still take it a block, this side and this side, this side and this side. Say one side is high voltage side, one side is low voltage side. This is unique, right? So, high voltage side is 11 kV, low voltage side is 440 volt. This is unique, but high voltage side can be connected to the source. If I connect a source here, then this will be load, right? I can connect the load here. So, in that case, we say this is a primary side. So, high voltage side in this particular is a primary side, and the load side is secondary side, right? Obviously, you can just make it different. So, this part you can remove, this part you can remove, and you can clearly put the other way around. You can put source here, this side, right, and the load here, this side. In this particular case, which side is primary side? Which side is connected to the source? So, this is now the primary side, and this is now the secondary side. But note, low voltage side and high voltage side, they have their identity intact. Okay, fine. The next is well, let's go in the next page. In the transformer, what is there? What do you expect to be there in the transformer? So, first is a magnetic circuit. Let us try to go into the transformer. It's a magnetic circuit, okay, and then you have winding wrapped into it. So, I would prefer different color, because I have the option to have diffuse different color here. Suppose this side you have this is right, okay, and this side I can put it something like this. So, this side is something like this. So, this is suppose 2 sides, okay, and then you can connect a source this side, source this side, right. So, this is a simple magnetic circuit. When we draw this magnetic circuit, so right, so we are trying to learn the principle of operation of the transformer. What is the target now? Principle of operation. Very quickly, let us just check what happens. If you check, of course, when you think of core, making a core, the core looks like, of course, core looks like this. It's a 3-dimensional structure, right? 3-dimensional structure, and the winding is actually wrapped all the way, right? So, you can clearly check the winding should all the way go over there, and then go over there, go over there, go over there, something like that. And this side also, it will come over there, and then it will go over there, and then go over there, go over there, go over there, and come back. Actually, this you have the core and the winding wrapped into it, right? For the time being, we are thinking of a simple configuration. One winding this side and one winding on the other side of the limb. This is never the case. We will come to that later. But well, to study the principle of operation, this is sufficient. Okay. So, if this is the case, you have a voltage source connected to some number of turns. You can say this is N1, this is N1 number of turns this side, this is N2 number of turns this side. Then what happens? First thing is, of course, when a current will be flowing, some current will be flowing through this because the voltage source is connected. Suppose I connect it, say this is my V1, I can say this is my V1, some current will be flowing, I can think of this current to be I1. If I put this way, we can think that this is to be I1 all the way flowing like that. And then clearly you can see that if the current is all the way flowing like that, then the flux will be produced. And now what we will assume, just for the convenience, I will actually move to a simple, and that is always done, simple two-dimensional structure. So what is that? So for the core, normally it is convenient. So instead of thinking of a three-dimensional kind of, this is enough to talk about a two-dimensional kind of structure. And then you have something like this, and you have suppose something like this, the two sides, and then what you are trying to do, you have voltage source here, right? And then assuming that, suppose this is my V1, some current I1 is flowing like that, and this current you can check the direction is something like that. You can just have the thumb rule, right? If you put the thumb rule, then you can see that the flux will be actually having a, we'll take a, this will be upside, will be downside, flux will have a path something like this, okay? And this flux is of course linking the other winding, okay? So then if we start from the flux quickly, if we start from the flux, say phi, so we assume that phi m sin omega t. If we think phi is phi m sin omega t, right? Whatever voltage induced here, this side and this, I am not putting any specific arrow, say I am putting just E1, just putting E1 here. So how about E1 here? We know that from Faraday's law, minus N1 d phi by dt, something like this, and you can clearly calculate this one as N1, and then this is phi m, and this is omega, and this is cos of omega t. You can always write that, and here you can write N1, and this is phi m, and this is still omega, and then I can write it in terms of sine, and this will be your pi by 2 minus omega t, you can write. And the next thing is sine minus theta is minus sine theta, so you put it N1 phi m, this is omega, and this will be your sine, and this will be your omega t, and this is minus pi by 2. So you can get E1. E1 is this. So if phi is phi m sin omega t, then E1 is E maximum value EM1, which is N1 phi m omega, and sine of, you can see that omega t minus phi by 2. Okay, so this relation is perfect, right? So we just write it here, so E1, we just write it here, E1 is EM1, just EM1, and this is sine here, and this is omega t, omega t, this is different angle, so difficult to write, omega t minus pi by 2, this will be there. Now if, and then EM1 is just EM1 is N1 phi m omega, N1 phi m omega. So let me write it. So EM1 is N1, this is N1 phi m and omega, right? If it is that, then clearly we can write E2, the voltage that can induce on the other side, this side, okay? So I switch to the pen. If I assume that E2 voltage will be induced here, why E2 voltage, why a voltage will be induced this side? Because, so this is not coming properly, undo, okay. So you can see that this side is E2, this side is E2, because the flux is linking this coil. If this is N1 number of turns, this is N2 number of turns, right? So the following, applying the same principle, because the flux is linking E2, change of flux, and the number of turns is N2. So, just apply the same principle. So, E2 will be minus of N2 and d phi by dt, d phi by dt, d phi by dt, right, and then you can just apply, you can see the final expression will be here. So, this will be EM2, this will be EM2, this will be EM2, this will be sine, this will be sine, this will be omega t minus pi by 2, this is pi by 2, this is pi, not omega, this is pi by 2. Okay. So, the phase angle relations remain same, E1 and E2, EM2 is only different. How about EM2, right, this side EM2 is, so we can write EM2 to be now N2 and this is phi m and this is omega, only the change is N1 and N2. Okay. Fine, right. So, for a transformer we can clearly see, if you check the expression. So, if you are interested in RMS values, so you can write E1 to be EM1 by root 2, right, and you can write E2 to be actually EM2 by root 2. E1 and E2 you can write, E1 is this, E2 is this, right, and from there we can go to, suppose this part we erase, this part we erase, right. So, you can clearly see that E1 is the next, so E1 is then, how about E1? EM1 by root 2. So, this is clearly N1 phi m omega, this is omega is 2 pi f, so you can write 2 pi f by this is root 2. So, that will be this 2 pi by root 2, this is 4.44, this is 4.44 and then N1 phi m f, right, and similarly E2 also will be root 2 pi, right, which is 4.44 and this is N2, this is phi m and this is f. So, E1 and E2 RMS values you can get. Clearly, if you check that, because this is the same flux is linking both N1 and N2, right. So, if you compare this E1 and E2, so if you check that E1 by E2 if you make, you can clearly see that this is N1 by N2, and this is turns ratio. Sometimes we say this is A, we say this is the turns ratio of the transformer, and which is A, right. So, now with all this, whatever thing we got, let us try to see the relevant waveforms, right. What I mean, so if I again if I try to just plot this waveform, if I plot this waveform phi, so suppose I just try to plot this waveform phi, so this is phi, and this one can be omega t or t, whatever it is, this can be omega t or t, right. Phi is a sine wave, so you can plot a flux sine wave, something like this. Okay. Then how about my E1 and E2? You can clearly see E1 is sine pi by 2 minus omega t minus phi by 2. So, lagging phi by 90 degree. So, if I try to find E1, suppose I put a different color. So, we can clearly see that this one and this one will be there. So, the E1 is actually something like this, E1 is something like this, right. So, this is E1, this is E1 and that was a phi, this is E1 and that was a phi. Okay. E1 and phi business done. The next part is how to know I1, how to get I1 from here, right. So, we E1 done, flux done, I1. So, if we assume the magnetic circuit to be linear, right. So, what do? We go to the next page quickly, right. We go to the next page quickly. So, what we do here, So, this is our suppose flux, this is the flux phi, and you can check that, we can always think this is B and H, this is BH characteristics of the material. We know that flux is nothing but B into A, P into A, right, and H I is nothing but I is HL, this is H into L by N, HL is Ni. So, clearly B and H, because A is constant area and L by N is also constant. So, in a different scale this will be your phi I characteristic, right. So, I can write that this is in a different scale. So, you can put that in a different scale, this is my phi and this is my I in a different scale, I can put it that way. Okay. And if I assume my phi I characteristics to be linear, so that is just a linear, then if flux is sine wave, right. So, sorry, so if this is not, if flux is a sine wave, then if we try to find, suppose this side is current and this side is omega t, if we, and this side flux and this side is omega t, suppose. So, for a definite flux, what we are trying to do, we are trying to find the nature of the current using the magnetization characteristics of the material. So, in the core, if you like to produce this flux, what kind of current you need? We are just trying to do that. So, you can see that when, the at say T1 flux is 0, current is 0. So, here you are at T1. When the T2 flux is peak, you can all the way go over there, current is peak, you can go to up to T2, you can all the way come over here. T3, right, this is T3, 0 again, 0, you can go to 0. T4 here, T4 minus this side. So, you can see that because it is linear and identical. So, some T4 you will get some value like this. So, clearly if I add this, so see if I add this, then I will get the nature of the current, and which is just identical to that of the flux. So, we can just conclude from here is, if flux and if this is this, then the corresponding current required to produce this flux is this, which is actually this. So, this is your current and this is a flux and current, they are in phase. So, if we go back the previous page, so if flux is this here, something like this, so the corresponding current will be in phase. So, you can check that this will be your I1. So, this will be your I1, the current that will be flowing through this. Okay. The next is, well, this is just a coil, and for the coil no resistance, nothing considered for the timing, no resistance, no leakage. So, current must be lagging V applied voltage by 90 degree. So, how would V? And because we have neglected, this is ideal case, we have neglected all resistances, leakage reactances, loss, magnetic circuit linear. So, clearly V1 and E1, right, V1 and E1, the magnitude wise they are same, but how would phase? If I1 has to lag V1, then obviously this V1 and I1, so you can clearly write V1 is actually minus of E1, V1 is minus of E1. And how would minus of E1? If we put that now, so this is just like this, this is just like this, right, and then this is peak over there. So, this is just V1, right. So, now let us check how it makes sense. For one point, see, because this is a coil and effectively this is an inductance, pure inductance, resistance neglected. So, the current this I1 must be lagging V1 by 90 degree, and we can clearly see that now V1 and I1 lagging V1 by 90 degree. So, that is perfectly valid. Okay. And then on the other side, when we apply Kirchhoff's voltage law here, V1 and E1, in a sense V1 is minus of E1, right. Effectively E1 is E1 when we say E1 is minus N1 d phi by dt, that is a voltage rise, and minus of E1 probably voltage drop, we can think that way, and voltage rise should be equal to voltage drop. So, V1 and E1, we apply the same voltage here, right, and from that, and we will maintain this convention all the way. So, what we will consider? We will consider V1 this side, and this one we will consider minus of E1 from here. V1 should be equal to minus of E1, and the current we can clearly see is lagging what is expected, right. But on the other side, E2 side, E2 is just minus N2 d phi by d2. So, if I try to put E2 here, what will because E2 and E1 E1 is minus. So, you can clearly see how about E2. So, if I put E2 here, so E2 is just minus N2 d phi by dt, only a scaling factor different. So, depending on N2 is more than N1 or less than N1, E2 will be different. So, you can clearly see that if I assume that step down transformer, so E2 will be less. So, you can assume that this will be your E2, this will be your E2. So, this will be E2, something like that. Okay. Perfect. Next, so with our conventions done, next let us consider now that the magnetic circuit is not non-linear, because if the magnetic circuit is linear, we can clearly see that flux and current. So, this was the flux, right, you can clearly see, and the corresponding current they are in phase. If the magnetic circuit is non-linear, what happens? So, to do that, we can go to the previous page, okay, next page, okay, and the next, okay, here. Now, if the magnetic circuit is not linear, what happens? So, we consider now on top of this we can do that. So, assume that because of saturation it looks like that, sorry, because of saturation it looks like that, right. So, this is because of non-linearity. The red part is undo that, I can put it in a different color. So, suppose we consider the non-linearity, okay, can we put yellow? So, then this will be something like this, and this will be something like this when we consider the non-linearity. And if you do in the way we have done, you start again from 0, you will get a 0 here, you get this point, and all the way when you go to the peak, you get same point, and again 0, you get to 0, same point, peak, go to the peak point. Zeros and peaks, they remain intact, but what happens in between? You can see that, you will see that this nature is something like this, no longer a typical sine wave that we got, something like this, right. This is because of the nonlinearity. If you split this into different harmonics, you will see you have a fundamental and you have a third harmonics predominant. Let us neglect the third harmonics part. So, still the fundamental will be in phase. So, we are fine with that, with these simplifications. Okay. So, we still say that this kind of nonlinearity introduced, your current will be this in phase. What happens when we consider hysteresis? When we consider hysteresis, quickly let us go to the next page, pages, and previous page is there. Okay, next page. Let's look at the next page. So, when we consider the hysteresis, then something interesting happens. What happens? So, now, so you have a flux still the same, sine wave flux here, and you can see this side, you can have now this one and this one, we say this is flux and current characteristics phi I. So, from flux using phi I characteristics, we will actually go to I omega t, I, the nature of the current omega t. What do we do? Well, the peak values are somewhere here, the peak values are somewhere here. If we now try to actually show the hysteresis part, so suppose this will be this, and this will be this, and this will be this, should be identical, something like this hysteresis method. And then what that when flux increases, it is this way, decreases this way. When the flux increases, you have to follow this path. When flux decreases, you have to follow this path. Now there are two different paths. That was all about hysteresis. And if you start again, checking. So if we now go to, so for this point, increasing 0 is this point. So you go to this point. And then now T1 here. So then you go to some time scale T1. T1 is peak value. So you are here. Peak value is somewhere here. So you can get somewhere here. And when 0 coming down 0 is this. So when it's 0, you can get already negative. And when again peak, when it is peak, you can get the same picture, right? Go all the way and same picture. And then you can have the next one again, it will be a repeat kind of things. Next one will be again, So this is, if I try to connect it, you have something like this, and this is, and this, something like that. The current nature is something like that. Well, undo. So this will be when it is, this is 1, 2, 3, 4, 1, 2, 3, 4. So by this time it will be again having the same value. So it will be something like this. The nature will be this. What is interesting here is, you have an in-phase component of the current created. So if you split this current that you got using the hysteresis, right, magnetizing characteristics of the material to have this flux, then you got this current, and this current, if you split it up, you get two components. The first component will be a peak value, something like this, right, this, and then this, and then this, a component this, and then the original component, right. If I put it red, the original component, which is actually this all the way, sorry, because this has to go, this undo, this has to go all the way, the peak values will be same. So it is something like this, right, and then it will be something like this, it will be something like this, and this will be something like this. So the current, sorry for my very bad drawing, but what is interesting or essential is, if I draw it here, if I draw everything here, so you can see that this is your original flux, this is original flux, this is flux, two components of the current. One component, the rate component is in phase with the flux, you can clearly see. So you have a component which is in phase with the flux, right, and you have a component, the blue component, which is leading the flux by 90 degree. So you have a blue component, yes. So we have which is leading the, so this is leading the inner flux by 90 degree, very small value, leading the flux, right? These are the two components, right. And if I put those V1, E1 here, what was the V1 last time? So V1 is actually this side. So if I put V1, see, if I put V1 V1 was, V1 was something like this. V1 was actually, this was V1, right, which was ahead of flux by 90 degree. So now you have two components of the current flowing through the coil. One is of course the rate components, which is predominant, which is again lagging V1 by 90 degree, but you have an in phase component which is in phase with the V1. Why the in phase component has come up? To account for the hysteresis, and V1 multiplied by I1, right, will be the hysteresis loss and integration. If you do it time domain, or you just do Phasor multiplication, V1 capital and I1, cos of angle is, theta is 0, cos theta is 1. So V1 I1 simply will give you the hysteresis loss, right. And then next, if we try to draw the Phasor diagram, next, okay, so we start with the flux. We start with the flux phi, okay, and then we have this side. We have E1, right? If it is a step down transformer, it will be less. We will have E2 this side, okay, and there will be one component of the current I phi in phase with the flux. How would V1? V1 is other side, V1, that must be equal to minus of V1, everything perfect. The main component of the current, which is lagging by 90 degree, right? And then you have small in phase component, which is accounting hysteresis loss IH, and then putting this together, you have now I1 that was flowing. I1 that was flowing. So this is your Phasor diagram. In transformer core, other than hysteresis loss, you have also eddy current loss. Eddy current loss, you all know, if you think of the core, you can just core area, you can think here, right? When the flux is oscillating, you can think the flux is oscillating. This is flux, some positive, this side negative, this oscillating. You can clearly see, you can clearly think of, because the core material is not insulating material, right? Iron, whatever you use over there. So you have the resistance is definite. So you can think that this outer loop, if you think, looks like a circuit, looks like one coil shorted, and then because that coil is actually inducing, going through change of flux, so voltage will be induced, current will be flowing. The current will flow in the direction to oppose the flux, right? So if it just let us take which direction to flow or current. So if I say this is the current, so I will put the current nature this way. I am not getting it. I would like to have a different color. Current one, this one, no, not giving it. I don't know. Anyway, I will just put the current. Suppose I arbitrarily put this current and this current. This I put the current, then it is same direction. You can clearly see that's the same direction. So it has to be opposite, or flux has to be reversed. So you can clearly see that the current direction will be this and this. The original one is wrong, and this current will be always looping. And then you can have n number of such loops, and the current will be flowing. Losses will be there. So that is eddy current loss. And what we normally do, we add another component in the same directions to account for the eddy current loss, and this is total. We say this is core loss IC. So core loss is hysteresis and eddy current loss. We will have much more in future classes. And this is the I1, which is the further time in the transformer. It's not loaded. You can clearly see that we are considering a transformer, one side and the other side. So we have just expressed this V1. We have just expressed this is as minus of V1, right? We have flux, and this is the current I1. Because no load is produced, we say this is I0. This is I0. So this I1 is nothing but I0. Okay. So we have, unfortunately, the time is not there. So you just summarize. We have just started transformer revision. Tomorrow again we have class. We will make it up, so overall transformer rating part we have learned. We have already shown you a transformer, small transformers, which is one side could be primary, another side will be secondary. Any side could be primary and secondary, depending on which side is connected to the source, which side is connected to the load. That way primary and secondary defined. We have understood the rating of the transformer, and then we have learned simple Phasor diagram after the no load operation. Thank you. And in the next class, we will study the equivalent circuit for the loaded conditions and other details. Okay.